All right. So, you see how there's writing all over this problem? This is momentum practice free response question 2, number 3. Yeah, I guess I got so excited about explaining this question to an empty room that I forgot to hit record. That's why you see all the writing. I'm going to, instead of rewrite everything, I am going to try to explain everything. My apologies for the little messiness here, but okay. So you have a block M here, block A with mass M, and it's going to slide down a frictionless set quarter circle and collide with block B, which has the same mass. And they're going to have an inelastic collision, not usually spelled this way with a space in between. It threw me for a moment, but they're going to stick together. And then they're going to slide along this friction place here with friction. So, not surprisingly, the first thing we want to know is the speed of this block just before the collision. We've seen this a few times if you've been doing them. And this is just the potential energy here being turned into the kinetic energy here through conservation of energy, and find the velocity from the kinetic energy. So what I said was the potential energy of block A at the top, which equals mgr. Wait, where'd the r come from? This height, it's kind of sneaky. It's the same as the r. They put the r off at an angle to kind of disguise that fact, but it's r. So that's what the height is. Equals the kinetic energy of A at the bottom, which is 1/2 mv of A at the bottom squared. So I set this equal to this. M's divide out, and I solved for the velocity of the block at the bottom. And I got velocity of block A at the bottom is the square root of 2gr. Cool? There's part A. Done. So tricky part, it's not tricky in the sense that we've seen this plenty of times, unless this happens to be the first problem you looked at, where we have an object at a ramp or a pendulum or whatever at a certain height stationary, and it turns into kinetic energy down here, and we have to find the velocity. We've seen that a lot. Okay. B. Determine the speed of the combined blocks immediately after the collision. This is pretty much straight up conservation of momentum. The initial momentum equals the final. The initial momentum was just in A, just before the collision, and it was its mass times the velocity we found back here at part A. Right there. Equals, they stick together. So now their mass of the object, now that they're stuck together, is double that, 2m. And I'm looking for this final velocity. So I solve this for the final velocity, and I get square root of 2gr divided by 2. All right. B, taken care of. C, determine the amount of kinetic energy lost during the collision. So we now know the mass and velocity of the objects after the collision. That's enough to get kinetic energy after. And we know the mass and the velocity before the collision, and that's enough to get the kinetic energy before. In fact, we already had the kinetic energy before. We wrote it right here, but we're going to keep it in terms of 2gr and everything. So before the collision, it's just block A, and its kinetic energy is 1/2. There's just one mass in this case because it's just block A, and then velocity squared. Well, the velocity is square root of 2gr. So if I square that, I just get 2gr. Cool? All right. Final kinetic energy. Well, now they've combined after the collision, so there's 2m for a mass. So I got 1/2 2m. Then this is the velocity that gets squared, so the square root here goes away, but I do have to square the 2, and that's why there's a 4 here. And they want the change in kinetic energy. Now, we should lose kinetic energy, not gain it in this case. So I set the initial minus the final. So here's your initial minus the final kinetic energy. And then there's just a lot of numbers that cancel out, 2's to go away and so forth, and it all comes down to this. I would be interested actually when they say determine the amount of kinetic energy lost, technically speaking, this is right. It's not simplified, but it is correct. And I would argue they would probably give you the point for that. And maybe it's even not a good idea to try to simplify this, because you might make a mistake and get an answer that they can't determine is right. I don't know. D. All right, so D, this is an old question. You can tell from the graphics. This is from a test years ago where they combined AP 1 and 2. This specific heat stuff, don't worry about it. You would basically take this energy and use some calorimetry and figure out, blah, blah, blah. But that doesn't mean we can't do E. It says determine the additional thermal energy that is generated as the blocks move from Y to P. Well, if you understand what friction does, it turns kinetic energy into thermal. So really, I just need to know the work done by friction. If I can tell you that, then that's the thermal energy. I just need the work done. And look, they give me the distance. That's a strong sign that work is going to be involved here. I just need to know the force. Well, they give me mu. Remember that equation that I promised you that nobody would remember? If you remember that I said that nobody would remember it, why didn't you just remember the equation? But anyway, that's this one. Force of friction is mu times normal force. But if you have, and I think I drew it here, if you have this 2m block on this horizontal surface, the weight and the normal force are the same because it's a nice horizontal surface. So it's really mu times 2mg, the weight of the blocks. So there's your force of friction. Force times distance. So there's your distance. L, they go little lowercase l here, and in their description earlier, they use uppercase L. Meanwhile, also don't ask me. Proofreading must not have been a thing back in '78. We'll put a negative on it. It doesn't really matter because this is the amount of heat energy lost, generated. Done. All right, I pushed record. Excellent.